Hello and welcome to the second video of the M2 chapter Projectiles. On the screen I start a question to review the previous video. A ball is projected horizontally off a cliff at 10 meters a second. So here we've got a cliff, we don't know how high it is, particle projected horizontally at 10 meters a second. And it moves freely under gravity, so gravity is the only force acting, which means it will follow a parabolic trajectory like this. What is its distance from its starting point after 2 seconds? Okay, let's say it's here after 2 seconds. And the question is, what is this distance here from its starting point to its point at t equals 2? To do this, we're going to need to find two different things: the horizontal distance it has travelled and the vertical distance it has travelled. And we'll have to do these as two completely separate calculations. So looking at the horizontal distance first, I'm going to resolve, take the direction to the right as positive, and if we're looking horizontally, moving under gravity, there is no acceleration. The initial horizontal velocity is 10 meters a second, and we're looking at when t is equal to 2, how far has it travelled. So I'll just call that s in my equation. So we've got s is equal to ut plus a half at squared, and of course with no acceleration this term disappears and we're back to our old friend displacement equals velocity times time. So we've got s is equal to u 10 times t 2, 20. And all of these have standard units, so that is 20 meters. Looking vertically, I'm going to resolve with my positive direction downwards. So we have acceleration due to gravity, 9.8. We have an initial vertical velocity of 0, and again the time is 2 seconds, that's the key point we're looking at, and we want the displacement. Same formula, s equals ut plus a half at squared, and this time the first term is 0, so we just have a half times 9.8 times 2 squared, and that will give us, if I put that quickly on my calculator, 19.6 meters. This is 19.6, and now we can find in purple the hypotenuse of this right angle triangle by doing the square root of 20 squared plus 19.6 squared. If I put that on my calculator, I get the answer 28.00 dot dot dot. They're not all zeros, so I'll put 0.0 and then write 1 dp to show that it was not an exact answer. And that is my final answer. In this video, we're doing a very quick application of a skill you have already done from M1 in this slightly different context. So we're going to resolve velocity components. Then in the next video, we'll take this idea, put them together to do this one. So although it's a short video, it's very important for the next one. As with forces, which is something you've done in M1, we can resolve any other vector, such as velocity or acceleration, into horizontal and vertical components. And we do this just by looking at some simple trigonometry. So, for example, if we've got a particle, and in M1 you looked vertically, that was fine. This way, that was fine as well. In the previous video, we've looked horizontally, and that was okay. Now we're talking what happens if it's coming out at an angle, let's say 40 degrees to the horizontal. And if the magnitude of the velocity is, let's say, 20 meters a second, then we need to be able to split this into its horizontal and vertical components. And it's exactly the same as you've done before with, as I said, for example, forces. Here in purple, the horizontal part, if I call this u, the initial speed, then I could call this maybe u subscript h for horizontal, or if you prefer I and J, or if you prefer X and Y, whichever one you like, just be consistent. Then I hope that you already know what I'm going to write here. This is 20 times the cosine of the angle 40 degrees. The vertical component, same idea, you can call this UV for vertical, or if you like the IJs, or if you like the XYs, again, be consistent. If you use this one, use this one. If you use this one, use this one, and so on. All of those, whichever one you're using, is 20 times the sine of that angle, 40 degrees. And the reason this is important in this chapter is because of what we said in the previous video about the horizontal and the vertical motion being independent. If you've got motion like this initially, you need to be able to split it into these two components, because this component, if your particle is acting under gravity only, this component will not change, it will remain constant. But this component will change over time because gravity will be acting on this particle and there will be a downward acceleration. So once you've got your two initial velocities, this will be used in the horizontal calculation, this one will be used in the vertical calculation, just as we had the two separate calculations in the starter question. The only difference is in the starter question, this one was 0. We'll do one quick example of this, and then we'll do a second example where there's just something else to talk about alongside this. So the first example, a particle is projected with velocity u, and you might notice this is a bold u to indicate that it's a vector. Same with I and j here, these are in bold. So u is equal to 3I plus 5j meters a second. Find the initial speed. Remember, speed is not a vector, speed is a scalar. And its angle of projection. This is a key phrase here in green. You might see this phrase in your exam. So to do this, we've been given the two different components. We've been told that the particle is projected with 3I meters per second, so that's in the horizontal direction, and 5j meters per second, so that's in the vertical direction. Which means on my diagram, it will be something like this. And just be careful to label your angle so that the examiner knows which angle you're looking at. So I'm going to call this u as a vector, and then when they say find the initial speed, I will write this in the magnitude symbol like this to indicate that this is the speed I'm finding, and you know how to do this, it's Pythagoras. Square root of 5 squared plus 3 squared is equal to square root of 34, or 5.83 to 2 decimal places. The angle of projection, you also know how to do this. Of course, this is, pretending the 5 is over here for a second, a little right angle triangle here. We've got the opposite over the adjacent. So tan of theta is equal to 5 over 3. So theta must equal 59.0 degrees to 1 decimal place. From your work in M1, you should remember that it's very, very unusual to write angles in radians in mechanics. Stick with degrees unless told otherwise. At this point, I think I could call this finished because I've indicated on the diagram where theta is, but if I wanted to be very careful about that, I could say 59.0 degrees to 1 decimal place to the horizontal. Or to the positive I direction or something like that, just to make it really clear what that angle is, because you could have found this angle and that would have been fine as well, so long as you were clear that that was the angle you had used. Second example, a particle is projected from a point on a horizontal plane with an initial velocity of 40 meters a second at an angle alpha above the horizontal, where tan alpha is 3 over 4. So this example is telling you the angle, but it's not telling you the angle explicitly. It's telling you the angle by giving you one of the trig ratios. Now, of course, what you could do is just do the inverse tan of 3 over 4 and get the angle of 36.9 degrees to 1 decimal place. But if your question wants you to find anything exactly, then that's no good because you'll be rounding that angle in order to put it into your next calculation. So what I'm going to focus on in this example is how to get around using an inexact angle if you want an exact answer. This is something I did in one of the Further Pure videos, but not everyone doing the M2 module will be doing the Further Pure modules. Okay, let's take a quick look at what it actually wants us to do. Find the horizontal and vertical components of the initial velocity and use them to express the initial velocity as a vector in terms of I and j, which are the horizontal and vertical unit vectors respectively. So what we've got is horizontal ground, particle projected at 40 meters a second at an angle of alpha above the horizontal. And we know that tan of alpha is equal to 3/4. The question is asking us to find the horizontal and vertical components. And as a question, that's actually quite easy. From what we've already said so far, you know that the green one here, the horizontal component, is 40 cosine alpha, and we know alpha is about 37 degrees, and the blue one is 40 sine of alpha. But in order to get these as exact values, we need to do something slightly differently. So let me put this on just to remind us what we're trying to get here. This is 40 cos alpha, and this one is 40 sine alpha. And yes, you could work those out very easily, but to get them exactly, we're going to do a little bit of trigonometric manipulation, starting with this statement here. And then at the end, we will put them together with i's and j's to give a final vector velocity. I guess I could put that on now to make that clear. That is I, and that's the j component. So, the crux of this example. How do we get cosine alpha as an exact value if this inverse tan 3/4 is not going to give us an exact angle? To do this, we need to remember what tan of alpha actually is. Way back at your GCSE level probably, or something equivalent to GCSE, you learned that the tangent and the sine and the cosine as well is a trigonometric ratio between the lengths of two sides of a right-angled triangle. So going all the way back to our friend, the right-angled triangle. Here, this is telling us that if this angle here is alpha, the tan of that angle is 3/4, and the tan ratio is opposite over adjacent. So the opposite is 3, and the adjacent is 4. Now I should emphasize that we're not claiming these to be the lengths as such. This is just a ratio between the two lengths. So this could be a 6 and this could be an 8 instead, and that will give you the same tangent value. It could be 30 and 40 or 300 and 400. That doesn't matter. But the ratio of these two things must give you a 3/4. We also know from past work that if the ratio of these two is fixed, the angle here is fixed, this 90 is fixed, then whatever these numbers are as you scale them up, if you did go 6 and 8 for example, then this length would scale by the same amount. So the ratios between these two, and these two are all fixed given the information we've got here in the triangle. So I can use Pythagoras' theorem to find the missing side. In this case, it's a 3, 4, 5 Pythagorean triple. So this is a 5. Now I've got all of the lengths of the sides as respective ratios, so I can find sine and cosine using the information shown. I know that sine of alpha is equal to the opposite divided by the hypotenuse. So the ratio there is 3/5. Whatever the values are, if this is a 6, this is an 8, this would be a 10, this would still be a ratio of 3/5. In the same way, we know that cosine alpha is adjacent over hypotenuse. So that would be 4/5. And if you started with the sine or the cosine here and you needed to find the tan, you could do the same process. Draw your little right-angled triangle, put the ratio numbers of the two you've been given onto their respective sides, find the third side using Pythagoras, and then use that information to find the other two trig ratios. Now all of that is an aside to say that we know cosine of alpha as an exact value. And if you did the inverse tan of this to find 36.869897 ... put that into the cosine on your calculator, you probably would not get this exact value coming out. I certainly wouldn't on my calculator, but doing it this way tells me that this is exactly 4/5. So I can put that in here. So this is 40 times the cosine of alpha, which I know is 4/5, which gives me a nice exact answer of 32 for the I component. In a similar way, sine of alpha is 3/5, so up here it's 40 times 3/5. And again, I end up with a really nice exact answer here, 24 for the j component. Now when I come to write my initial velocity as a vector, I can write u is equal to 32I plus 24j. I would emphasize here that my question didn't really require that of me. It didn't use the word exact at any point in here. It is implied to use this method when they give you the information like this, but it might just be that they didn't want to write a decimal value for alpha. However, what I would say is if you see the word exact, give your answer as an exact value, then this is a really good way of doing this without ever actually needing to know the value of alpha. So I hope that's been helpful for you. The concept in the video I think was very straightforward, splitting your velocity into its two components. We'll use that a lot in the next video. Maybe I'll see you there. In the meantime, you can practice using questions from exercise 1b.